All right, guys, welcome back. So this is the second video. Now, last video we talked about all the different ways that we could prove a parallelogram, and we're actually going to do a proof of the very last one because doing the proof of this one will also show you kind of how we use these to prove parallelograms. Okay, so because we can use any of the other three that we've proven so far, or that we've used so far in order to prove this one. We just can't use the theorem itself to prove it. So we're actually going to prove that if one pair of opposite sides of a quadrilateral are both parallel and congruent, then it must be a parallelogram. So here we're given that AB is both congruent and parallel to DC, right? And we're trying to prove that this is in fact a parallelogram. Okay. So think about what we need to do in order to do this. So in the last video, we talked about, okay, I had that diagonal there. I knew it was congruent to itself. We kind of talked about the alternate interior angles, and somehow or another that led to opposite sides congruent, so on and so forth, right? So here's kind of why. So my whole goal here is to set this thing up to use one of these other theorems that I've kind of already talked about in order to prove it's a parallelogram. Or my whole goal could be to prove that the other set of sides has also got to be parallel. Whichever way you want to do this, there's actually more than one way to do this proof. I'm going to choose the method of proving that the opposite sides are congruent, right? And then I'm going to use this theorem, and the only reason I'm doing it this way is because I want to show you how to use these theorems. There is an easier way to do it using just the ideas of parallel, but we're going to use that first theorem anyway. Okay, so my whole goal then is to show, right, so if I'm going to do it that way, I want to show, so WTS, want to show, right, that AD is congruent to BC. Okay, and so that's my whole goal here to show, because that's the way that I need this in order to get, to use my last step, which is that if both pairs of opposite sides of a quadrilateral are congruent, right, then the quadrilateral is a parallelogram. Okay? So, here we go. My first statement is always going to be my given. Right, my given in this case is that AB is congruent to DC, right? And, oops, I don't know why I did that. And AB is also parallel to DC. Okay? That should be everybody's first step. Now for the second step, we're going to use one of these two ideas. In fact, the only one that we're really going to use, or one of the things that we can say in here, is that since our diagonal DB is there, let's introduce that into the proof. And let's just say that, well, DB is congruent to itself by the reflexive property of congruent. Okay, so right now we've just shown that, hey, we got that one. Okay, actually I don't need that third line. Now that we have two of the pieces, now we want to introduce some sort of angles in here, because again, our whole goal was to also get, or part of our goal was to get the triangles congruent, so let's do that now. And again, since we're using the idea that these two guys are parallel, that's why we needed them to be parallel, is that allows me to say that this angle and this angle are congruent because they are alternate interior angles. So in here we can say that angle ABD is congruent to angle CDB by the alternate interior angles theorem. Now that I've got the angles congruent, I'm allowed, so I've got a side, an angle, and a side congruent in here. All right, that allows me to say that the triangles are congruent by side, angle, side. So I'm just going to use the same letters that I used before. So I'm going to say triangle ABD is congruent to triangle CDB. All right, and that's by side, angle, side. So now that I've got the sides congruent, and again, from this point, so no matter which way I do this proof, this is the step that I have to get to. I have to prove that those two triangles are congruent. Right? That's the only way to work on this next one. So again, I could go the route where I say, hey, you know, angle ADB is congruent to DBC now by CPCDC, right? And then I can just say, well, that also means AD is parallel to BC, and that would just be using the definition of a parallelogram. But I want to use, right, the theorem that I talked about. So now I need to have I can get my part in here that I wanted before, and I can say that, hey, you know what? Because those triangles are congruent, that tells me that side AD is congruent to side CB or BC. Okay, and that's just by CPCTC. So now I have BC congruent to AD. I can use, my last step is simply just saying parallelogram ABCD, right? And that's because if both pairs of opposite sides of a quadrilateral are congruent, then quadrilateral is a parallelogram. Okay, and I know that looks a lot more lengthy of a reason than we've kind of given in the past. All right, but we can find ways to shorten that. I'm going to kind of throw that out throughout the rest of the semester as far as how to shorten it. But for now, I wanted you guys to get practice kind of writing it so you understand what it's really saying. All right, and how we can use these ideas and those properties is just kind of determining whether or not it is a quadrilateral, and then we're the key part to this one is we're going to justify our answer. So we're going to use one of the theorems that we just introduced in order to determine whether or not these are parallelograms using just the given information. So number 9, right, it is a parallelogram because we have both sets of opposite sides congruent. So for number 9, I would just say yes, right? And then it would be that same reason. So I would say if both pairs of sides congruent, then it's a parallelogram. Okay, and that would be my reasoning. For number 10, okay, so we have one set of sides that are obviously parallel, that's what those arrows indicate, and now we're also given that their measures are 3. Well, if they both have the same measure, that would mean that they are congruent. So this would also be a yes, and this would actually be the theorem that we just proved, right? So if one set of sides are congruent and parallel, then it's a parallelogram. You see how I'm kind of cutting out some of the keywords since we already know we're talking about a quadrilateral, so on and so forth, okay? For number 11, what we're given, right, is that we have a side length of 4 and a side length of 4. So yes, these two sides are congruent, but we have no other information, right? So we can't use any of the theorems that we talked about, right? So in this case, we would not have a parallelogram, okay? Because I don't have any sets of angles, I have no other sides, I have nothing like that. In number 12, okay? So when we're looking at this, we're given that, hey, we have this diagonal is kind of getting bisected, and we also have that this side and this side are congruent, okay? And then some other key pieces of information that we might have in here is that we have these two guys are congruent, okay, because they're vertical angles. And so we can actually prove that this guy would indeed be a parallelogram, and part of that reason why is because now that tells me by CPCTC that this piece is congruent to this one, right? And we can actually say yes, right, if both diagonals bisect each other, which they do in this case, right, then parallelogram. Okay, so it is indeed a parallelogram. And we're going to use the exact same reason for number 13, except for we're already given it. So yes, if both diags bisect each other, then parallelogram. All right, and then in my last one, right, what I have is number 14. What I have that these two guys are supplementary, which is great. That would make these two sets parallel. However, the one thing that we don't have is anything else. Okay, so I have no idea about other opposite sides. I have no idea about opposite angles. I have nothing really else other than the fact that, hey, the top and bottom are parallel, these two angles right here are supplementary, but I have nothing, like I need one of these angles in order to even say that. I need this one either congruent to 105, or I need it to, like, I need something of that matter. I need it to be 105 degrees in order for this to work, but we can't prove that. We don't know it. So realistically, this is not a parallelogram, okay? For number 4, for these next two, what we're going to do is we're going to find x and y, right, so that they're both parallelograms. So different than the examples that we've seen in the past, right? We're not assuming that these guys are parallelograms already. So what we have to do is we have to say, hey, you know what? What do I need for these guys to be in order for them to be parallelograms? Well, since we're given a whole kind of slew of angles in here, right, rather than try to make them all supplementary, what we're going to do is we're going to say, hey, you know what? Okay, we're going to use this idea, right, that if both sets of opposite angles are congruent, then it's a parallelogram. Okay, so we're going to use that idea to set this up. What that would mean, right, that 8x minus 8 would have to equal 6x plus 14, and it would have to mean that 6y plus 16 is equal to 7y plus 2. So now that's given us enough algebra to be able to actually solve for both x and y, which is nice. Okay, so I'm going to solve for x here by adding 8. And again, the geometry comes from the setup, guys, not the algebra. Okay. So now when I add 8 to both sides, I get 8x is equal to 6x plus 22 minus 6x minus 6x. 2x is equal to 22 divided by 2, and x is therefore equal to 11. Okay. For the second one, again, I'm going to subtract 6y first. Why not? I get 16 is equal to y plus 2 minus 2 minus 2, and I get y is equal to 14. So if, again, the way that you kind of want to see this is if x equals 11 and y is equal to 14, right, then we'd have a parallelogram. That's kind of how you want to look at this. So we're not assuming that this is a parallelogram first. We're showing that if those two are that way, then we do, in fact, have a parallelogram. All right, we're going to use the same thing. And we're going to kind of keep that same idea going with this next one. All right, we're going to say, hey, you know what? Since we're given all these sets of opposite sides here, all right, we're going to say if both sets of opposite sides congruent, then it's a parallelogram. Okay, so that's the idea that we're using, which means that we need to have this side congruent to this side, so which means that 2x plus 3 has got to equal x plus 7, and likewise 3y minus 5 has got to equal y plus 11. Okay, solving these each individually, minus x, x plus 3 is equal to 7, minus 3, x is equal to 4, right? And then we're going to add 5. Notice here that I'm kind of changing up the way that I do it each time, just because it doesn't really matter which one I add first to both sides, right? It's just I'm adding or subtracting. I'm balancing the equation either way. Then I have 2y is equal to 16, divided by 2, y is equal to 8. So again, kind of the way that you want to think about this is if x is equal to 4 and y is equal to 8, all right, then we'd have a parallelogram. Okay? And that's kind of how we use these theorems and these ideas to kind of make this stuff work, guys. All right, thanks for watching. Good luck on the assignment today.